Hello mathematicians and welcome to the last lesson for Unit 6. We are on Lesson 10, Rectangle Proofs, and you are going to see a lot of similarities with rectangle proofs and parallelogram proofs because a rectangle is a parallelogram. But let's talk about how we can apply our new information on rectangles using like what we know about parallelograms. So up first, do we know the difference? And let's see if I can move myself so I'm not in the way. So quadrilateral, four-sided shape, okay? Up here, we've got our example of a quadrilateral. Then we go down to a parallelogram, a four-sided shape whose opposite sides are parallel. And then we get even more specific and we're working with, a shape whose opposite sides are parallel, but all of our angles are 90 degrees. So we kind of have this fixed shape here. Now, do rectangles have congruent diagonals like parallelograms? Let's look at a proof. So we've got over here our rectangle, and we are working with A, B, C, D. And once again, where our diagonals cross, that is at point O. And we are told that triangle ABCD is a rectangle. This is what we know, and we're trying to prove that AC here, AC, and let's actually swap it for a highlighter. So we're trying to prove that AC here is going to be congruent to BD here, okay? So we're trying to show that these two diagonals are congruent to each other. Now, the first bit of information that we always work with when we're doing a proof is the given information and the definitions. This, I've kind of combined them a little bit. So step one, given that ABCD is a rectangle, by definition, it is also a parallelogram. Okay, so by definition, we have a parallelogram. So that means that opposite sides are congruent. So that means that DA is congruent to CB and that DC is congruent to AB. Okay, that is all information that we know to be true. Now, by definition of a rectangle, we also know that all of our angles here are right angles. And we have the right angle congruence theorem that tells us that if we have right angles that are, if we have, right angles and we're comparing them, right angles are all congruent. Right angle congruence theorem says all right angles are congruent. Now, I want to show that AC and BD are congruent to each other. So I just labeled everything on my triangle, but I want to focus on only two kind of triangles within my rectangle here. So I'm going to focus on DA and CB, just so that my picture that I'm drawing doesn't get all muddled. So right now, if you guys can see here, we've got this triangle here, and it's DAB. And right now we are showing that we have a right angle here, and we have a side, and that is congruent to our other triangle, which is going to be oops, I erased the whole thing. Let's undo, there we go, which is CBA, there we go. And we also have a congruent side and a right angle. Now, in order to use one of our triangle congruence theorems, we need to show that either our hypotenuse is congruent or we need to show that another leg is congruent so we can use side angle side. Now, we are trying to show that our hypotenuse are congruent to each other. So that means we don't want to use that. We want to show that this side, these are congruent to each other. But if you notice, in our DAB here, we have AB, and then we have CBA, and we have BA. We're using the same leg here. And if there's a theorem or property that we use that says if two things are the same, then they are congruent, and that is step 3 here, our reflexive property of congruence. It's going to show that AB and BA are congruent to each other because they're the same side, which gives us our side angle side, our side angle side. Look at that. So by side-angle-side congruence theorem, we know that CAB and CBA are congruent to each other. From there, we can show that by CPCTC theorem, that also means that our third side here is congruent to each other, right? That means that AC and DB are congruent to each other. So once again, we're working with triangles to show that our diagonals are congruent. Okay, now what does that mean that we know about parallelograms and rectangles? Okay, we know that opposite sides are parallel, so that means we have AB is congruent to DC, we have DA is congruent to CB, and then same thing here, right? We have our congruent, or our parallel sides, okay? Parallel sides, opposite sides are parallel. We also know that opposite sides are congruent, so we can use congruence theorem, or congruence markers here, or little tick marks, to show that our opposite sides are also congruent to each other. Now, the last little congruence that we have is that our opposite sides are congruent to each other. And realistically, right, for rectangles, all of them are congruent to each other, but specifically we can state that both of them have opposite sides that are, or opposite angles, excuse me, that are congruent to each other. The last little two little things are that consecutive angles are supplementary. So remember, if we have like our alternate, oh, why do I keep drawing it on the same side? There we go. These guys, consecutive, same side, right? That means that these are supplementary. So when we add them up, it equals 180 degrees. Okay, same thing goes here. These ones are 180 degrees. Lastly, our angles bisect each other. Okay, so that means that DO and OB or BO are congruent to each other, and then CO and AO are congruent to each other. And it goes the same for this parallelogram here. Okay, so these are things to keep in mind because we are going to do one more big proof here. But first, let's talk about how we can use this information of consecutive, of diagonals being congruent. How do we use this information? Well, the first thing that I know to be true is that they're bisectors, right? Our diagonals bisect each other, so that means that DO and BO are the exact same length. So how I can use this is, right, we have a 3x plus 5. If we kind of have two of them, right, the 3x plus 5, if we have two of these, then, let's move me down here. Okay, that should be equal to the entire length. And in this case, right, we have 9x minus 2. So if we add these up, right, then these should be, or if we take this and we add to this, then these should be the same. We can also simplify this by saying 3x plus 5 is equal to 9x minus 2. Okay, and this means that we can now solve for x. We have two equations and a single variable. We can solve for x. So to do this, if I'm working here with the multiplication, and let's talk about both sides, and then I will, or both options here, and then I will solve for 1. So if we're working with this 2 of the one side, this 2 is being multiplied by everything on the inside. So that means that I have to take 2 times 3 x's, which turn into 6 x's, and then 2 times 5, which turns into 10. The same thing goes here, combining like terms. I have 3x and 3x turns into 6x, and then 5 plus 5 turns into 10. So it doesn't matter which one makes the most sense to you. They're both equivalent. We can either add 2 of the same things, or we can multiply. Now, we want to solve for x. So now we have these equations equal to each other. We want to get our x's on one side and our numbers on the other side. I always pick my x's side to be the side that has more x's, so it's going to be this side. So that means I'm going to get rid of my x's on my left side here. Okay, and that means that I have 0 x's, but I still have the 10. And this means that I have 3 x's and I still have this minus 2. I don't want numbers on my x's side, so this is a minus 2. I'm going to do the opposite and I'm going to add 2, but what I do to one side I have to do to the other. So that means that I am left with 12 is equal to 3x. We just want a single x. This is 3 times x. To undo multiplication, we divide both sides. So that means that I get x is equal to 4. And then I can plug them in to solve the side lengths, right? So I could just replace using that substitution, right? I can replace a 4 in 4x, and then that gets 12 plus 5, which means our side length here is 17. For one part of our diagonal here, it's 17. For both of them, right, it would be 34. So, and let's write it right here, 34. And we can double check that by once again plugging in a 4. Let's look at our proof in proving that parallelograms are diagonals. Now, this proof is in your book. We're just going to go through and talk about it, see what's being applied, make sure we understand all of the parts. Now, we are given that quadrilateral ABCD is a parallelogram, and we're given that the diagonals are congruent to each other. We want to prove that this parallelogram is in fact a rectangle. So we know that this is a parallelogram, and we know that DB, this one here, is congruent to AC. Okay, and these are kind of off kilter, but we know that these two are equal to each other. Now, by definition of a parallelogram, opposite sides are always congruent. So that tells us that DA and CB, and then DC and AB are congruent to each other, right? That's by definition of a parallelogram, opposite sides are congruent. Okay, and then something else we know is that if we wanted to work with triangles again, remember we love working with triangles because we have the triangle congruence theorems, we can look again at our DAB triangles, or BAD in this case. They chose to do BAD and ABC. But these two triangles here, we can look at them and show once again that our triangles are congruent. This time they did by side, side, side because we're told that our diagonals are equal to each other. So that means that we have our congruence theorem, right, that states, and let me redraw this, maybe this will be helpful. So we're told that our diagonals are congruent. By definition, opposite sides are congruent. That means that by reflexive property, we can show that this side is congruent. And so then we have our triangle BAD, which is going to be congruent to our triangle ABC here, okay? So we've just did a really quick triangle congruence to show that these two triangles are congruent to each other. Now, that information gives us the opportunity to state that angle BAD, so this one right here, which I'm not going to do as a right angle because we don't know it's a right angle yet, but we can do this to show that BAD and ABC are equal to each other. By CP/CTC, well, not even just equal, they're congruent, right? Specifically, they are congruent. Now, moving on to the second part of our congruence, our proof. Okay, we have all of this information. We know all of this to be true. Now we want to show that BAD and ABC, those angles are 90 degrees. So then we can show that it's a rectangle, right? So by definition of congruence, okay, we said that angle BAD and ABC are congruent. By definition, that means that they are equal to each other. Okay, by definition of congruence, they are equal. Now, we have the consecutive angle, right, of a parallelogram are always supplementary proof that we have done in the past, right? We're given this information. Consecutive angles are supplementary. And what that means is that, let's switch up colors here. Okay, this angle and this angle are going to be equal, well, okay, so now that we know that angle BAD and ABC are congruent to each other, then by definition of congruence, we can say that those two angles are equal to each other, okay? So the next step is we're going to do some angle manipulation in order to show that these angles are in fact 90 degrees. Now, here, right, we know by definition of a parallelogram, working with definition of a parallelogram, that we have these opposite sides that are parallel to each other. That means that we can actually treat side AB here like a transversal. And we know that consecutive angles of a parallelogram are always supplementary. So that means in this case, we have two consecutive sides here, right? And that means that these two sides are supplementary. So that means that our angle BAD and our angle ABC, when we add them up together, we get 180 degrees. However, we showed that they're equal to each other. So we can substitute in for ABC, BAD again. And we're given BAD plus BAD equals 180 degrees. Well, if we have two of those, they're equal, right? Bad's equal to bad in this case. That only means that we can split up bad equally one way. And that means that the measure has to be 90 degrees in order for these to be split evenly. Okay? So what does that mean? It means that basically, right, if we know that BAD is equal to 90 degrees, and ABC and BAB, if ABC and BAD are equal to each other, both of them have to be equal to 90 degrees. And if opposite angles of parallelograms are equal, then that means the other angles have to be 90 degrees. So now we have four 90-degree angles that we're working with here, okay? And that means that we have a parallelogram with four 90-degree angles, and therefore we have a rectangle, okay? So first we proved congruence using a triangle sum theorem, which was side, side, side. And then we're saying, well, if these two angles are congruent to each other and consecutive angles are supplementary, then we have to have 90 degrees. Okay, so that is the proof for proving that this specific, right, parallelogram is in fact 90, or a rectangle, because it has 90-degree angles. Let's move on to a couple of quick practice problems, and then we will be all done. So we are given this triangle again, rectangle again, ABCD. And we want to ask which of the following statements, once proven, would prove that the diagonals are congruent. So we want to show that BD and AC are congruent to each other. And so we're asking, what triangles do we need to work with in order to make that true? The first triangle they state is this ADC is congruent to CBA. Now, this is a great triangle congruence theorem, right? We could prove that these triangles are congruent to each other. However, we want to show that this side here, DB, is congruent to AC. And in this proof that we would be showing with these triangles, we aren't working with DB. We won't be showing that that is true. We'll only be showing that AC is congruent to AC, and that is not enough information. So this one here cannot be our statement that would show that DB and CA are congruent to each other. Now, the next one that they've given us here is that BCD, so BCD here is congruent to DAB. And we have the exact same problem. This time, we're ignoring this CA diagonal right here. We would be able to show that DB is congruent to DB, but that's it. And that's not what we want. We want to show the diagonals are equal to each other. So let's confirm here that ADC and BCD would be correct. So A, D, C, okay, and B, C, D. There we go. We've hit both of our diagonals here. So that means that we could use this statement to show that our diagonals are congruent because we are talking about each one of the diagonals. Let's do a quick example. This is our last practice problem. Let's do a quick example of showing that, or I guess working with the diagonals to show, or to solve. Working with the diagonals to solve. That's what we're doing. We're solving. So we're given these, we're given rectangle ABCD. We want to find the length of AC, given that AO is equal to 9x minus 1, and DO here is equal to 6x plus 7. We have diagonals. Diagonals bisect each other, right? So that means that 9x minus 1 is equal to 6x plus 17, okay? DB and AC are congruent, and so are their little segments here that intersect with O, which is our the point at which we bisect. So these two things are equal to each other. And then we can just simply solve a multi-step equation in this case, right? So first up, we want to figure out what our x's side and what our number side is. X's for me is always the side with more of them. The other side is always just automatically the numbers. So I want to get rid of my x's on my number side. I'm going to do that because we have positive 6x's. I'm going to subtract 6x's from both sides here. That gets me 3x minus 1 is equal to 17, right? We've got rid of our x's. We're left with just a 17. We want our number side to be the only side that has numbers, so we need to get rid of this minus 1 by doing the opposite, which is adding 1. Okay, so that gets us 3x is equal to 18, and this is a 1, by the way. We just want to talk about a single x. Okay, we have 3 x's. We need to do the opposite of what is happening here, which is multiplication, which is divide both sides by 3, and we are given that x is equal to 6. We were asked to find the length of AC, which is this whole length here. So first what we need to do is find the length of AO, and then we can times it by 2 to find the length of AC. So we can plug this, this x back in. We're starting with the equation 9x minus 1. We can substitute in the 6 in, which is going to get us 9 times 6 is 54 minus 1, which is equal to 53. So one of these little sections is 53. If we times it by 2, we can get the whole length of AC, which is going to be 106. So AC here is 106. Okay? Alrighty, guys, that is it for the very last lesson. Please, please, please reach out if you have any questions. And until next time, have a fabulous day.